All right, welcome back. I decided to just do it on the same day. So what we didn't get to cover quite yet, and so to wrap up sections 1.6 and 1.7 is on transformations. So transformations apply to both discrete and continuous variables. And so that's why I wanted to kind of put them off and then show you everything about transformations in one go. So transformations, and you know what? Instead of you watching me write it out, how about I pause it, write out a little bit so we can talk about it, and then we can keep going. That should be good. Okay. So I tried to keep it all on the same screen. And so what we're going to talk about is transformations. Basically, what we're doing is we're taking one random variable x, and then we're going to transform it using some function into a new random variable y. And so here I wrote, suppose you have a random variable x whose properties are described by a Cdf, which we denote by a capital F, right? And now we need to highlight that this is for x, right? The random variable x. So fx and possibly either a PMF, probability mass function, that's for a discrete random variable, right? And so we can denote that by a lowercase px of x. Or a PDF is if you have a continuous random variable, right? And that's the probability density function, which we denote by fx of x. So transformations are really important. So one important question is that if you define a new random variable where y is some function applied to x, right, g of x, using some function g of x, what is its CDF? So what is the cumulative distribution function of y, fy of y? And if applicable, meaning whether it's discrete or continuous, right? The PMF, that doesn't look like a y. I'm going to fix that. Py of y. And you know what? I'm going to clear this one up too. My y's and my x's look similar, right? So, so if applicable, the PMF py of y, or the PDF if you have a continuous function, fy of y. We assume that, and we're going to say that g is single valued, which is basically saying that it's one-to-one. And so one-to-one, remember, means that a function is invertible. So that's good. We're actually making room for many-to-one, but usually we just stick to one-to-one. But I will say here, we assume for simplicity, that g is what we call single valued. And invertible. I'll do a little definition of single valued below, but I'll finish the sentence first so that we can define. So we can define a function x, which is the inverse of g on y. Okay. So here, single valued means that each point in the domain has a unique value in the range. Has a unique value in the range. Oops. Almost combine those two words, the range. Okay. One-to-one or many-to-one. but usually we just stick with 1-to-1, right? So that's why I'm going to highlight that, because that's usually what we're focused on. Good. So first thing I want to do is talk about transformations on the Cdf and the Pmf. They're going to be a little bit easier, and then we'll eventually work up to the PDF, which is the continuous probability density function, right? And so transformations of the Cdf and Pmf. Okay. And how can I make this like a little, like a subsection? How about that? What's nice is that the Cdf and the Pmf, they're both probabilities. Okay, and so we're going to start with the Pmf, because the probability mass function is just the probability of x equaling some value x, right? And so both the Cdf, which we denote by fx of x, which is the probability that x is less than or equal to x, and the Pmf, which is px of x is the probability that x equals x. So many x's. Both the Cdf and the Pmf are probabilities. Okay, this makes their transformations pretty straightforward. Not in the beginning, obviously, but once you see what we have to do to work over a PDF, then this will be a lot simpler. Okay, so this makes their transformations pretty straightforward. Okay, so that's going to be the hiccup once we hit the PDF, is that, okay, they're not actually probabilities anymore, right? Because if we have a continuous distribution, there's no probability at a single point. We can only talk about intervals. Intervals exist, but not single points anymore. So for a discrete random variable, oh, I forgot to move my mic closer, but I think probably doesn't matter. Can you hear me? So for a discrete random variable, the Pmf transforms as follows. Py of y, so we're going to work backwards here, is the same as the probability that y equals y. That's fine. We can just say that for any variable, right? Px of x is the probability that x equals x. So the same goes for y. So far, so good. So then what we're going to do is we're going to say, okay, well, y is actually going to be a function of x, g of x. So the probability of g of x is equal to y. Now what I'm going to do is, remember, g has to be invertible. And so now I'm going to shake out the x here and move this g. I'm going to take the inverse of g of y. So then this becomes the probability of x being equal to g inverse of y, right? So then this is the same, right? So now that I'm talking about a random variable x, right, that's the same setup as I had up here, except now I'm taking the px, right? So not the py anymore, px of G inverse of y. So this is going to become px of G inverse of y. Okay, so here I just want to highlight where things went and where they came from. So the same thing here, right? I can go backwards and I can say, okay, if I want the probability that x equals this inverse of y, right, then that's the probability that I put, or that's the function that I put inside this probability. Okay? And then x just maps here to here. Okay? So the same setup for both of these. Okay. What does that mean? It means I can take this PMF of x, right? So the one that we know already, and I can just apply it to the inverse. That's fine. Okay. What about the CDF? Now remember, CDF, the cumulative distribution function, has that inequality, which makes things a little bit trickier. Not bad, but a little bit trickier, right? Because now, now I have to think about, okay, what's the probability that G of X is less than or equal to Y, right? So things are a little more complicated. For the CDF, oops, that doesn't look like for the CDF, since we have to deal with the inequality. Since we have to deal with the inequality. G of X less than or equal to Y. What we're going to have to focus on is, okay, so if G is increasing, right, then it's going to behave differently than something that's decreasing, right? So if G is increasing, meaning that if we took the derivative, it would be positive, or if it was decreasing, then of course, if we took the derivative, you had a negative slope. So that's all we're talking about here. So if G of X is an invertible function, which we're assuming it is, an invertible function, it must be either monotonically increasing or monotonically decreasing, okay? Because you can either have this kind of steady increase, right? Or not necessarily steady, it can kind of vary, but overall it has to be increasing, and same thing, or it could be decreasing, but you can't be going back and forth, because then it's not one-to-one, right? Because then it wouldn't be invertible. So if G of X is in an invertible function, it must be either monotonically increasing which means that G of X increases as X does. G of X increases as X increases. Or monotonically decreasing which would mean what? It means that g of x is decreasing as x increases. G of x decreases as x increases. Okay. So the situation is going to be a little bit different depending on if it's increasing or decreasing. Okay, but if it is monotonically increasing, let's start there because it's a little bit easier. So if it is monotonically increasing, g of x less than or equal to y is equivalent to x less than or equal to g inverse of y. Okay. And that's because, so this inequality stays the same, right? And that's because g of x is increasing as x increases. So maybe I'll highlight that here. Inequality, stays the same. Okay. Whereas in the next one, the inequality is going to be different. So what we're going to find that fy of y, starting with kind of where we want to end up and kind of working backwards, we find that that's the same as the probability that y is less than or equal to y. Replacing y with g of x, that's the same as the probability of g of x less than or equal to y. Now, when I take the inverse, right, and I invert this here, I get the probability that x is less than or equal to g inverse of y. So that's where this kind of mapped back. There. Okay. So that's going to look the same as the probability that x is less than or equal to x, but replacing x, the lowercase x, with g inverse of y. So then we get fx of g inverse of y. All right, same setup as before, and we can just map it back to, okay, so then I take that CDF function for x, that random variable x, and I apply it to the inverse of g on y. Okay. If it's monotonically decreasing, if it is monotonically decreasing, g of x less than or equal to y is equivalent to, if I take the inverse here, is equivalent to x greater than or equal to g inverse of y. So again, I want to highlight in the same way, right? The difference here is in the inequality, right? And so now we have a different inequality. Now x is going to be greater than the inverse on y. So what we're going to have is we're going to have fy of y is the probability that y is less than or equal to y. That's still the same setup as we started with before. So we start on the same train and we say that, okay, I'm going to replace my y with g of x. So then the probability of g of x is less than or equal to y. And then this is where it changes, right? And so here we see that we have the probability that x is greater than or equal to the inverse of g on y. So here I want to show that that's what happened here. Okay. We're not used to talking about the CDF in terms of being greater than some value. So in order to turn it back into some form of a CDF, a cumulative distribution function, it's all the values down below. So what can we do? Well, here we're basically giving the area above some point, right? So then 1 minus that would give us the area below that point, right? So we can use that same trick, although it's really not as obvious as it used to be, right, for us. But we do it. So 1 minus the probability that x is less than g inverse of y. Notice here, I didn't include the actual inverse because that's included up here. And so that's a little bit of a difference here, but in general, it has the same kind of layout. And so here, remember, we can think of this as a limit. So 1 minus the limit. I'm going to use the weird notation just so we can get used to it a little bit. As x kind of comes up on the inverse of g on y of fx of x, right? We are talking about x, right? So x is our variable. So that's why we have fx of x. And we are using x here as a placeholder because x is approaching the inverse of g on y, right? And then we're taking 1 minus that limit. If x is a continuous random variable, this becomes what? Well, then we don't need to deal with limits anymore, right? Then we can just say that fy of y is 1 minus fx evaluated at g inverse of y. Yeah. Good. So now we've seen transformations of the PMF, we've seen transformations of the CDF, the cumulative distribution function, both for discrete random variables, and that's when we would use the limit here, because then we might have, steps to deal with, or if we have a continuous random variable, then we can just evaluate the CDF. What if we want to talk about the transformation of the PDF, right? We said, oh, that's going to be tricky. So here we go. So transformation of the PDF. And what did I do? I think I underlined in orange or something. Yeah. I'll match it. Okay. So here, if x is a continuous random variable and we know the PDF, which we denote by a lowercase fx of x, that probability, that's not a probability anymore. It's a probability density, right? But it's not actually a probability. We can't talk about the probability at a single point anymore. So that becomes the problem. So if x is a continuous random variable described by a PDF, fx of x, the PDF is not a probability, but a probability density, Oops. Having been defined as the derivative of the CDF. As the derivative of the CDF. So that's cool, because then what we can do is we can take, if we have the CDF, we can take the derivative of it to find the PDF, right? Or if we're working the other way, if we have the PDF but not the CDF, then we could integrate the PDF to get the CDF, right? And so we're going to have that relationship. Just like we had for the PMF, the probability mass function, to find the cumulative distribution function, what did we do? Well, we added up the probabilities up to and including some point, right? And so same thing with the probability density function. So again, we're going to have to consider monotonically increasing and monotonically decreasing situations. So what I want to do is, just so we have it in the notes, I'm going to write it out in the notes. We'll talk about it briefly, but the important part is the final results that we arrive at. So that I will write out with you, but for this, I'm going to pause it, write it out. We can talk about it. Okay, so, right, we're looking at the transformation of the PDF. And so what we said was, all right, we're going to have to consider the monotonically increasing function as well as the monotonically decreasing function separately. Okay, so again, we have to look separately at the case where the transformation function g of x is monotonically increasing and monotonically decreasing. What we're going to find is that we're going to be able to develop each of them individually. So that's why I said this is less important. And then we're going to put it together into one function. And so that's what we're going to be working with, right? But the reason why we're able to develop into one function is here. So if g of x is monotonically increasing, meaning that the derivative is greater than 0 over the region of interest, that's kind of implied. So I didn't write that for the second portion, but so the derivative is positive. We can use the chain rule to show that, okay, well, the PDF, right, is denoted by a lowercase f. So now I'm talking about the PDF of y is going to be the derivative of the CDF of y. Luckily, we just developed the CDF of y if g of x is increasing, right? And so we said that, okay, well, if I have the function, the CDF of y, then I can take the derivative of that and I can find the PDF of y. So then if I do take the derivative with respect to y of the function that we just developed, right, fx of g inverse of y, that's what we said fy of y was, right, if we had a transformation. So now I'm replacing fy of y with itself in terms of fx of g inverse of y. And then to show that I'm taking the derivative, I'm taking d dy, right, the derivative with respect to y. I'm going to rewrite that as, okay, well, I can apply the chain rule and say that the derivative of the outside is just going to be the derivative of fx, okay, evaluated at the inside, that's g inverse of y, okay, times the derivative of the inside, which is the derivative with respect to y of g inverse of y, okay. So that's just the chain rule. And so what we can say is that, well, I know the derivative of fx is actually the PDF of x, right, fx, evaluated at G inverse of y. Okay, great. And then we do something weird and we say that, okay, I'm actually going to end up dividing here by G, the derivative of G evaluated at G inverse of y. Okay. Now I'm completely drawing a blank. I was okay with it a minute ago, and so I'm sure I'll get there again. But anyways, this is what it ends up being. Okay, so you take the derivative of G divided by or times evaluated at the inverse. Man, long day. So anyways, so we can do the same thing if G of X is monotonically decreasing. And so that means that the derivative is going to be less than 0. So if we set it up the same way, we can say, okay, well, if I start with what I want, fy, so the PDF of y, that's going to be the derivative of the CDF. We just found the CDF. It's 1 minus fx of G inverse of y. Notice that I'm using that continuous version because that's what I'm dealing with, right? I'm talking about the PDF. So then if I take the derivative with respect to y, again, I take the derivative of a constant, that's going to go away, right? That goes to 0. But then I have to apply the chain rule again. So I have this negative lurking out front, right? And so I have, which I'm actually going to sneak down into the denominator, and you'll see it kind of go away. This is negative, right? Because it's decreasing. Okay, and so the PDF has to be positive, and so that's why we have this negative here, but we're going to adjust for that in our general formula. And I'm trying to get there as quickly as I can, dare. So that negative is just because it's decreasing. So again, I can take the derivative of the CDF, yep, evaluated at the inverse of y, and then the derivative of the inside is the derivative of G inverse of y with respect to y. So then I can summarize this again, right? And this little negative just went down into the denominator, and otherwise the numerators, try to have them on the same page here, the numerators are the same. So we're going to leverage that in our summary. And then what we're going to do is the denominators are essentially the same, except I've got a positive and a negative depending on if it's increasing or decreasing. And so what we're going to do is we can summarize this with one single equation. We can summarize this with one single equation. So what we're going to say, and this is the important one, so maybe I'll highlight that here. Okay, because this is the one that we're going to use. So as long as this one's okay, then you're good. Fy of y is going to be, so the PDF of y is going to be fx, so the PDF of x evaluated at G inverse of y, divided by, if we take the absolute value, then we don't have to deal with that positive, negative business to adjust for negative outcomes because we have a negative slope, right? And so if we take the absolute value, then we don't have to deal with that. And so that's what we're going to do. G prime of G inverse at y. Make sure I have the absolute values here. Okay. So what we could do is we could rewrite this as a kind of a new function here. And this is the version that we're going to be using. So we rewrite this as fx of G inverse of y times the absolute value of d dy G inverse of y, oops. I wanted to have it all over dy. It doesn't matter, but I want it to match what I have here. Yeah. This here is called the Jacobian of the transformation. This is not as bad as it looks, okay? So it's gonna be, and maybe I should bump this D kind of closer, a little bit closer, looks weird otherwise. It's gonna be the derivative of the inverse function with respect to y. For now, we'll just call it the Jacobian, oops. It's Jacob, the Jacobian of the transformation. Yeah. So sometimes we'll just call it dx dy, and I'll show you why in just a second, right? And so also written dx dy. Yeah. Because x is g inverse of y, right? And so dx dy would be the derivative of the inverse of y with respect to y, right? Assuming a transformation is one-to-one, which we're going to assume, okay? Of course, assuming a transformation y equals g of x is one-to-one, we follow these steps. We follow these steps to find the PDF of y. What you're going to find is that once you've done a few of these, it's actually pretty fun. Not in the beginning, though. Definitely not in the beginning. But once we've done a few, then you'll get the hang of it. So the first step is going to be to find the support of y. Now, we haven't used the term support, but it's basically the domain. Y is a random variable, and so it doesn't really, domain doesn't really apply, but we call it the support, and I think of it as the domain. So basically, what can I put into y, right? What can I reasonably put into y? And so here, find the support of y. That's basically, and I'm not comfortable saying it is, but I'm going to say that it's basically the domain. Step 2, you have to solve for the inverse of the transformation, basically solve for x. Solve for the inverse of the transformation. So that is solve for x in terms of y. In y equals g of x, obtaining x equals g inverse of y. So notice here, you're going to have x is some value, right? The inverse evaluated at y. And so then your next step is to find the Jacobian, which we usually just denote by capital J. And so that means just find dx dy. Okay, find the derivative of the x that you just found. And then 4 is just to construct the PDF. So put the pieces back together. And so that's going to be Fy of y is Fx evaluated at G inverse of y times J, the Jacobian. So let's have a look at an example here. If we let Fx of x be 4x to the 3 if x is between 0 and 1 and 0 elsewhere, that's a PDF of x, right? And so 4x to the 3, I know between 0 and 1, it's 1 to 1, just kind of remembering what it looks like. Or you could use Desmos if you're not sure, right? You can map it in Desmos. And if you don't know what Desmos is, I'll show you just quickly here. It's this kind of, it's this free graphing app. So if you do 4x to the power of 3, right, between 0 and 1, then you can see, now you can clearly see that it's 1 to 1. It does have some quirks, like, oh, I'm having a trouble zooming in. It does have some quirks, but not bad for free, right? Just for sometimes I need to map stuff out to just quickly see what it looks like. I'm not one of those brains that just knows what a function looks like. That's crazy to me. So often I'll just throw it in Desmos and just kind of get an idea of what I'm dealing with. Right. So it's reasonable to think that that's going to be 1 to 1. Okay, so and it is. So then what I'm going to find is well, I need the transformation. Let the transformation be y is going to be the negative log of x. I'll clean up this y because it doesn't really look that good. Here's a really important note. In statistics, the only log that we'll ever use is the natural log. And I know that's confusing because if you come from a math background, then we always specify, right? Log, when we write it, log is log base 10, whereas if we mean the natural log, then we use ln. But in statistics, we only ever care about the natural log. And so just for kind of clarity, we just write log. And that's confusing, but as long as you keep that in mind, that the natural log is the only log we'll ever use. So in statistics, so I know when I teach, pre-calculus and whatever, when I introduce logs, they get so upset with me because I'll slip up and read the ln as log. And kind of vice versa. So I call them both logs. But in statistics, we only ever use log base E. So usually, or ln, right? But we write log. Or maybe we write and read it as log. Right, so for clarity then, here, this log is actually referring to the natural log. Okay. That's going to be important, and that's why I wanted to do this one. So why is that going to be important? Well, it's important for finding the inverse, for one, right? So the first thing I want to do is I want to find the support of y equals negative log x. So the support of y equals negative log x. Well, what's that going to be? Just thinking about logs, I can only take logs of positive numbers. So I can't take the log of 0. I can't take the log of a negative number. So it's going to be 0 to infinity. That's just for us to keep in mind in case we try to find the negative log of something else, something outside that. Second thing is if y is the negative log of x, notice that I did transition to lowercase letters here. It's not terribly important, but when I'm solving in terms of just variables, I like to just switch to lowercase letters. So then if y is the negative log of x, then the negative y is the log of x. To solve for x, right, then what do I have to do? I have to take e to the power of both sides. So e to the negative y is e to the log x. And just to keep it on the same page, I'm gonna give myself one more line to work on here. So e to the negative y, oops. And you know what? E to the log x is just going to drop down to x, right? That was the goal. So, and I'm trying to solve for x here. So x is e to the negative y. Yeah. So what I'm doing, the step that I'm completing here is solve for x. So then I have to find the Jacobian. That sounds hard, right? But because I just solved for x, what I want to find is dx dy. That's just the derivative of x with respect to y, right? And so here, I want to find the Jacobian dx dy. So dx dy in this case is the derivative of x, which is e to the negative y. But e to the negative y, the derivative of that, I have to use the chain rule, right, is going to be itself e to the negative y times -1, right? Derivative of negative y with respect to y is -1. And so I get dx dy is negative e to the negative y. Okay. So now, the Jacobian is technically the absolute value here. So how about we do this? The absolute value of dx dy, well, that's just going to be e to the negative y. Right. Drop the negative. Okay. So step 4 is, oh, that looks weird. Step 4, now I'm going to put it back together, right? We said that what? Fy of y is, and let me just copy this here. Copy. So I don't have to scroll around so much. Fy of y in this case is going to be fx of g inverse y, which is going to be what? It's going to be e to the negative y. Because why is that? X is e to the negative y. Right. So really here, g inverse of y is x, right? And so x is e to the negative y times the absolute value, oh, kind of weird multiplier there, the absolute value of negative e to the negative y. And you know what? I already did it here. So typically I would get sloppy and I wouldn't do it here in this step. I would do it here in this step. But because we already did it, let's see here. Then I'll have times e to the negative y. And I'll clarify here what I said. X is g inverse of y. And we found x is e to the negative y. Right, so that's what that link is. So now, this Jacobian was actually, and just so you can see it, maybe in orange, the Jacobian was actually the absolute value of negative e to the negative y. I just don't want you to get confused with e to the negative y and e to the negative y. It's just because of how derivatives of e work, right? It's not going to be the case always. Remember, we're trying to find the PDF of f, but we had the PDF of x. So the PDF of x was, where is it? fx of x is 4x to the 3. Okay, so 4x to the 3, I can use that for x between 0 and 1, but that's okay. So now this becomes 4, but x is e to the negative y to the power of 3 times e to the negative y. Right? So then this becomes 4e to the negative 3y plus negative y, right? Exponents, touching on everything today, which is going to be 4e to the negative 4y, right? Negative 3y minus y is negative 4y. Ta-da! We did it. Nice work. And I'll end it there. And I'll see you next time. Bye.